This is AP Physics C 2005 Mechanics exam problem number 2. Okay, so problem A asks to find an algebraic expression for the gravitational force between Saturn and one of its moons. So to find the gravitational force, we just use the equation Fg is equal to gravitational constant times the two masses, the mass of Saturn and one of the moons, so m Saturn and the mass of the moon, over the radius, which is the distance between their centers of mass, squared. Okay, and then problem B asks to use your expression from part A and the assumption of circular orbits to derive an equation for orbital period t as a function of orbital radius r. So that means, because it's in a circular orbit, you can set f centripetal equal to fg. So mass velocity squared over radius equals what we found for in part A. One of the r's can cancel on both sides, and the mass of the moon can cancel, leaving velocity squared equals gravitational constant mass of Saturn over the radius. And we don't know what the velocity is, so we can use what we are given, the orbital period and the orbital radius, to find the velocity. So velocity equals distance over time, and the distance that the moon must travel in one orbit is the circumference of that orbit. So using the radius to get that is 2 pi r to find the circumference, and in a time of one period, which is t. And that's velocity. So plug that into this equation down here, and we get 2 pi r over t all squared equals gms over r. And solving for t, because we want a function of t as a function of r, we get t equals the square root of 4 pi squared r radius cubed over gravitational constant and the mass of Saturn. Part C asks, which quantities should be graphed to yield a straight line whose slope could be used to determine Saturn's mass? So we already have our equation, t equals and this equation has the mass of Saturn right here. So we need to find an equation where the slope is just constants and the mass of Saturn, so that we can derive the mass of Saturn from the slope in that graph. So we get rid of this square root by squaring both sides. And this is the slope of the graph, and these are the two things we should graph on the lines. So this is our t, the period squared is our y value, and the radius cubed is our x value, with the slope right here with the mass of Saturn inside of it. So we should compare time squared to r cubed on the graph. For part D, we use the data given in the table, orbital period t and orbital radius r, to find the quantities that we need to graph. So earlier we found we were going to compare time squared and r cubed. So just take all the t values here and square them and put them in the graph, in the table over here. And do the same for the radius, but this time cube it. And then fill in the table. And here are all the values that I already solved for. For part E, it tells us to graph all these quantities on a graph, label the axes with the variables used and appropriate numbers to indicate the scale. So our y values are time squared, which should be in units of seconds squared, times 10 to the 10th, because that's what all of our second values are, what power our second values are to. And the x value is r cubed times, which is meters cubed times 10 to the 25th. And we find that the highest values for both of these is 6. So starting from 0, 1, 2, 3, 4, 5, 6, 2. So now we just need to plot our points from the data on the data table. So here, 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 and all the way up here. And then create a best fit line, which we can use later to find the mass of Saturn. So from here, best fit line all the way up through here. And that would be our best fit line. So then problem E, or problem F, says using the graph, calculate a value for the mass of Saturn. So extrapolating some points from our graph, or the slope of, we can use the slope of this graph to find the mass of Saturn. So slope equals, and now we must extrapolate points on this graph to find the slope. So we're going to use one point right here, extrapolate from there, and one point up here, with a y value of about 1.4 times 10 to the 10th second squared, and 1.4 again down here. And up here, it's going to be about 5.4 and 5.6. So slope should equal y values, the change in y over the change in x. So 5.6 times 10 to the 10th minus 1.4 times 10 to the 10th over 5.4 times 10 to the 25th minus 1.4 times 10 to the 25th equals 1.05 times 10 to the negative 15th, about. And we know that the value of the slope should equal, from the equation, t squared equals 4 pi squared over gms r cubed. We should know that the slope should equal, when time squared and r cubed are compared, the slope should be that for the graph. So this value for this 1.05 times 10 to the negative 15th, that value for the slope should equal 4 pi squared over gravitational constant times the mass of Saturn, which we're trying to find. So 1.05 times 10 to the negative 15th equals 4 pi squared over gravitational constant, which is 6.67 times 10 to the negative 11th times the mass of Saturn, which we're trying to find. And algebraically, we will find that the mass of Saturn is equal to about 5.64 times 10 to the 26th kilograms.